We had 3 feet of snow and built snow tunnels to connect our yard to neighbors' yards. This was recalled by Fox Weather senior data specialist Shane Brown about the famed nor'easter of 1996. Nor'easters, formidable meteorological phenomena, primarily afflict the northeastern United States and Atlantic Canada with their potent winds and substantial snow or rain. These storms, capable of significant disruption and damage, necessitate precise predictions for effective management. Historically, the evolution of forecasting methodologies and technologies has markedly enhanced the accuracy of these predictions and the communication of associated uncertainty. The endeavor to forecast nor'easters, though they weren't commonly referred to as that, commenced in the late 19th century, initially depending heavily on ground observations and pattern recognition. The introduction of radar technology in the mid-20th century significantly advanced meteorological capabilities, enabling more effective observation of weather patterns. The 1960s ushered in the era of satellite meteorology, revolutionizing forecasts by providing comprehensive atmospheric views. In recent decades, the pivot to computer models has been pivotal, utilizing extensive meteorological data to anticipate nor'easters' behaviors days in advance. Regular updates to these models have refined their accuracy, underscored by historical data that enhances their predictive precision. Forecasting nor'easters has historically been fraught with challenges, but recent decades have seen significant advancements in accuracy due to technological and methodological enhancements. Initially, estimates of storm paths and intensities were rudimentary. The advent of sophisticated numerical weather prediction, or NWP models, which assimilate data from satellites, radars, and ocean buoys, has substantially increased forecast precision. These models are adept at simulating complex atmospheric interactions, thereby enhancing forecast timeliness and accuracy. Leveraging these techniques, one notable example of improvement between the 20th and 21st centuries is a one-day gain in predictability of mean sea level pressure and 500 HPA height in the northern hemisphere that was found in one study. As technology has progressed, the margin of error in predicting nor'easters' paths and strengths has notably diminished. Up until the 1980s, nor'easter prediction was so primitive that they didn't even recognize them as a separate category of storm. But recently, in one study, they found that 2 of the leading nor'easter prediction models, machine learning, or ML, and generalized linear model, or GLM, both had median absolute percentage errors of around 70% today. Moreover, GLM, the more advanced recently created model, does significantly better in predicting, quote, high-impact events, end quote, which in the study was over 300 outages, with one notable example being the devastating October 2011 nor'easter, which served as a case study for the paper. The quantifiable impacts in forecast accuracy are a testament to the advancements in meteorological science, which continue to push the boundaries of predictive capabilities. The capacity to make accurate estimates in nor'easter prediction hinges significantly on the sophistication of predictive models and the quality of input data. Ensemble forecasting, which employs multiple simulations with slightly varied initial conditions, is the primary method for assessing potential outcomes, thereby enhancing the reliability of forecasts. These estimates' accuracy relies heavily on comprehensive atmospheric data. The inherent complexity of nor'easters, characterized by rapid intensification and unpredictable tracks, poses substantial challenges to predictive accuracy. Specifically, nor'easters' dependence on very sharp temperature gradients between 2 adjacent areas causes the greatest uncertainty on these edge cases, where one neighboring town can get slammed with heavy snow/wind, while another neighboring town just gets a bit of rain. This was the case in January of 2015, when New York City was expected to get over 2 feet of snow from a nor'easter, but instead just got a few inches, while Long Island ended up getting over 2 feet themselves. Nevertheless, the potential for accurate predictions remains high, with some researchers speculating that improvements in predicting these outages could rise to roughly 80% of median absolute percentage error, again limited by the highly fickle nature of these sharp temperature gradients that nor'easters exhibit. Uncertainty in nor'easter predictions stems from various sources, including initial condition errors in models and the incomplete understanding of complex atmospheric processes. The dynamic interplay between the ocean and atmosphere, especially in coastal zones where nor'easters often intensify, adds to the unpredictability. Efforts to mitigate these uncertainties involve enhancements in observational technology and modeling techniques. High-resolution models and more detailed data from improved satellite and radar systems have refined initial model conditions, crucial for accurate storm prediction. Despite these advancements, however, some degree of uncertainty is inevitable. However, one study identified that focusing specifically on precipitation type and density, in addition to potentially combining the aforementioned ML and GLM techniques, are great ways that predictions moving forward could reduce uncertainty. Evaluating the accuracy and uncertainty of nor'easter predictions involves retrospective analysis and real-time verification, utilizing metrics such as mean absolute error and root mean square error. These evaluations are crucial for assessing model performance and making necessary adjustments. Historical comparisons are integral to this evaluation, providing a benchmark against which current model performances are measured. This analysis is complemented by real-time data during active storms, allowing for immediate model adjustments. Looking at historical examples, for instance, one study looking at the efficacy of dominant models used in a sample of 5 of the most devastating nor'easter ice events between 1994 and 1997 found that the models, quote, did not give acceptable prediction accuracies, or defined as less than 50% absolute percentage error in predicting the density of deposited ice, whereas applying the same metric on new models used between 2005 and 2018 instead The accuracy actually improved to over 70%. On a more practical note, though, although collecting data for estimating nor'easter prediction accuracy is much too technical for me or you to do without proper equipment, we can still look at regular online publications on weather channels to compare prediction accuracy ourselves, such as the one here, which compares two models' predictions on the left to their actual outcomes in the image on the right. Finally, communicating the uncertainties of nor'easter predictions is critical for public preparedness. Meteorological agencies employ probabilistic forecasts and visual aids, such as uncertainty cones, to convey potential storm impacts effectively. These tools are instrumental in helping the public visualize the range of possible scenarios and prepare accordingly. Moreover, the language used in forecasts is carefully crafted to emphasize uncertainty, aiding public understanding of the fluid nature of storm predictions. The effectiveness of these communication strategies is continuously evaluated through public feedback and social science research, ensuring that they meet the needs of the community. One example study found that in one sample message demanding evacuation for predicted nor'easter in an area, people rated their understanding of the message an average of 6.36 out of 7, and their likelihood to actually evacuate an average of 4.52 out of 7. Thus, the effectiveness of these communication strategies is continuously evaluated through public feedback, ensuring that they meet the safety needs of the community overall. So that's nor'easters in a nutshell.